At the D2L site, I've posted a handout, and just for your convenience. It has this problem we just solved, and then it also has this problem here that I just included. This problem is very similar to one of the other homework problems. And by similar, I mean almost the same, except for the resistances have been changed and the voltage across the battery has been changed. But other than that, it looks like the same circuit. So let's finish up by looking at this circuit here. Now, because we're always talking about the same times, I'm going to be able to use this, a lot of what's on the board here. Part A is immediately after the switch is closed. Well, immediately after the switch is closed, the capacitor is still empty. We haven't had time to charge it up. And so that means the voltage across the capacitor is zero, which means the capacitor is acting like a wire. So let me redraw this circuit. I've got a battery that's 180 volts. That's pretty hefty. And then I come down here, and instead of the capacitor, I have a wire. And then I have a 15 ohm resistor, and that's R1. And then I have an 8 ohm resistor, and that's R2. And then I have a 2 ohm resistor, and that's R3. And then I have a R4 that is 30 ohms. And what we're asked for is the current, magnitude, and direction through the battery. Well, I know the direction right away. The direction is up. Conventional current leaves the positive terminal of the battery and comes back to the negative terminal of the battery. But what about the magnitude? Well, in order to find the magnitude, I need to find the equivalent resistance. The one resistor that would replace that mess. Okay? Well, I've got an 8 and a 2, that looks like a 10, so that top side looks like 15 ohms in parallel with 10 ohms. Well, remember what we do when we have parallel paths that aren't the same resistance. We look for a common denominator. The common denominator between 15 and 10 is 30. So I can write the 15 as 2 30s. I'm leaving off the units there just to make things less messy. I can make a 10 ohm resistor with 3 30s. So this is exactly the same as that, which is exactly the same as the top half of this circuit. And now I can say I've got 5 paths that are all equal. They each have 30 ohms on it, and so the resistance is going to be the resistance of one path divided by the number of paths, or 6 ohms. Okay? Now, that means that this whole circuit looks like that. Okay? So this is going to be 36 ohms, 180 volts. If I use V equals IR globally, this becomes the equivalent resistance of the circuit. This becomes the battery voltage. This becomes the current through the battery. And if I solve that for the current through the battery, I get 5 amps. Now, we want to know the voltage difference across R3 from this point A to this point B. Well, I can use Ohm's law locally, where I'm just finding the voltage from A to B. It's the current that flows from A to B and the resistance between A and B, which is R3. Now, in order to do that, I need to figure out how the current splits right there. And then it comes back together right here. I've got 5 amps going in, but that 5 amps splits. Now, here's where this method that I taught you comes in really handy. If I have 5 amps coming into that junction right there, what it sees are 5 identical paths. There's no reason to choose one path over the other. So what I'm going to get is 1 amp going there, and 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 1 amp going there. Now remember, these 230s here are this 15 ohm resistor, so that means I got 2 amps going that way. These 3 paths, these 330s, represent that 10 ohm resistor, so I'm going to have 3 amps going that way. That's one way to look at it. Another way to look at it is that the difficulty of these 2 paths are 3 to 2. They're in a 3 to 2 ratio, okay? And that means that the current's got to split in a 3 to 2 ratio with the larger chunk going to the easier path. So I'm going to have 3 amps going down this path and only 2 amps going down that path. Now remember what we're looking for. We're looking for the voltage difference across R3. Well, that voltage difference across R3 is going to be the current that flows through between A and B through R3. That's 3 amps times the resistance of R3, which is 2 ohms, and that's going to give me 6 volts. Okay? Now, let's go to part B. A long time after the switch is closed, that capacitor is full. It acts like an open switch. And so now I have 180 volts driving current. Over here, I've got an open switch. And then I've got this R1, R2, R3, and R4, and then back. Now, in this case, the current is all going to flow through R2, R3, and R4. And that means, since this is 8 ohms, and this is 2 ohms, and this is 30 ohms, that what this looks like is 8 plus 2 plus 30, or 40 ohms, with 180 whoops, wrong symbol, volts. Now if I use V equals IR globally, this is going to be 180 volts, is going to drive current through 40 ohms. That's going to give me a current through the battery of 4.5 amps. And it's going to again be going up out of the positive terminal. Now, what about the charge stored on the capacitor? Well, the charge on a capacitor is just equal to the capacitance times the voltage across the capacitor. So what we need to do is find this voltage across the capacitor. Well, this open switch was the capacitor. It acts like an open switch or a gaping hole. So if I want to know the voltage from here to here, I look away from the sun. I don't look over here, I look at the parallel branch. Well, if I have 4.5 amps flowing across from here to here, that would be 10 ohms. Let's call this both A prime and B prime. The voltage from A prime to B prime is going to be 4.5 amps times 10 ohms, or 45 volts. Now, what's the voltage across R1? Well, there's nothing flowing through it, so this is going to be 0 volts. And so that means I'm going to have 45 volts here. Well, that answers my question. The charge is just the capacitance, which we're given in the problem as 1.5 farads. Remember, farad is just a fancy way of saying coulombs per volt. And then I multiply that by 45 volts, and I get 67.5 coulombs. Okay? Now, you'll get something different in your homework problem because you've got different resistances and different battery. Now we get to a part that makes this problem a little bit different than the first problem. Remember, I told you there were 3 times that we could talk about. There was an A, a B, and a C. The last time that we can talk about is after the switch has been closed a long time, right after you open the switch. Just like it takes time to charge up a capacitor, it takes time to empty a capacitor. And so if I leave that switch closed long enough for it to get charged up, in this case charged up was 45 volts. That's full, okay? If I leave the switch closed for 5 weeks, it's going to stay, the voltage across that capacitor is going to stay 45 volts. Now, as soon as I open the switch, that capacitor is going to start to discharge. And it's eventually going to drain away to 0, empty. But that takes time. So if I look right after you open that switch, the capacitor acts like a battery. So if I were to draw that circuit now, opening the switch takes the battery right out of there. The battery is no longer part of the circuit. And so all I've got now is a capacitor that's got 45 volts across it, hooked up to a 8 ohm resistor and a 2 ohm resistor and a 15 ohm resistor. And because I charge this up with the positive charge on the side of the capacitor closest to the positive terminal of the battery, it's going to be charged up like that. And now that 45 volt battery, that really is a capacitor, is going to drive current around that loop. And now the R1, R2, and R3 are in series. And so that means if I use V equals IR, I'm going to have 45 volts pushing current through 8 plus 2 is 10 plus 25, plus 15 is 25 ohms. And that's going to give me a current of 1.8 amps. Now, we're asked to find the magnitude and direction of the conventional current through resistor R1. Well, the magnitude is going to be the same through R1 as it is through R2, as it is through, this is R1, this is R2, this is R3. Again, old guy. So it's going to be 1.8 amps, whether I'm talking about through R1 or R2 or R3. It's just going to be going up through R1, down through R2, and down through R3, because it's running clockwise around that loop. Now, what if I want the voltage difference across R4? Well, let's look at R4 here. When I open this switch, R4 is just out flapping in the breeze. It's not part of the circuit anymore, just like the battery. And so there's nothing flowing through R4, and so the voltage across it would be it has no current. And the current through R1 is going to be 1.8 amps up.